Okay, we're going to talk about another method for determining the stability of the equilibrium for a linear system of differential equations. And this is called the trace determinant method. We already have a method, right? We know the eigenvalues will always tell us what's going on with the stability in terms of whether we get a sink, a source, a saddle, a spiral, a stable spiral. Those will always work. But we will see going forward, there are times it is nice to know about this method called the trace determinant method in situations where we are unable to find the eigenvalues. We'll see that a bit later. And for now, we can think of this as sort of an alternative method, a way to check our answers. If you understand it, it can actually be faster. You don't have to factor an ugly quadratic equation to determine what's going on with the stability. So here it is. So first of all, the definition, what I mean by a trace of a matrix is just the sum of the main diagonal entries, A plus D. And we usually abbreviate that tau. Delta is the determinant of just the original matrix, not with the minus lambdas there. So that's just AD minus BC. And we abbreviate that delta. So let's look at, this is every matrix, right? This is a general 2 by 2 matrix. So we're looking at what happens every single time you do the determinant of A minus lambda I. You would end up with this, A minus lambda times D minus lambda minus BC. If you FOIL that out, you're going to get a lambda squared. You're going to get a minus A lambda and a minus D lambda. So we can make that minus the quantity A plus D lambda. Okay, we're just combining those two terms. And then we'll end up with an AD minus a BC. That's right there. Notice this is the trace. A plus D is the trace. And the last four things here, AD minus BC, that is the determinant. So even if you just know this can make your life a little bit easier. Instead of, I don't know about you, but I've had some times where when I'm FOILing this out, I miss a minus sign or something like that. The quadratic you will always end up with when you have a matrix is going to have the form of lambda squared minus the trace times lambda plus the determinant. So you could go straight from your matrix to the quadratic by just finding the trace right there and then doing a quick determinant calculation, and that will go there, and then you can go on to factoring it. But there's more to this. Okay, what would the solution be? Well, I'd have to use the quadratic formula. I would get the negative of b, so the negative of negative tau, plus or minus the square root of b squared, tau squared, minus 4 times a, which is 1, times delta over 2. And of course, the negative of negative tau is just tau. So it's tau plus or minus the square root of tau squared minus 4 delta over 2. Now there's a lot we can interpret with this. Okay, for one thing, as we've seen, sometimes we get real eigenvalues and sometimes we get imaginary eigenvalues. So we can tell pretty quickly now, my eigenvalues will be real. The only way they'll be real is if this part under the square root comes out to be greater than 0. Technically greater than or equal to, but we're not going to talk about eigenvalues where you get repeated eigenvalues. That's not in this course here. So really it'll just be greater than 0 here. And for something you're going to see later, I'm going to solve this for delta, and that's the equivalent to saying delta is less than 1/4 tau squared. On the other flip side, your lambdas will be complex if this part comes out to be less than 0. If tau squared minus 4 delta comes out to be less than 0, that turns into delta is greater than 1/4 tau squared. Okay. Now, some more things we can learn about this. Okay. If delta is less than 0, if delta is less than 0, think about this. If delta is less than 0, that means this part is going to be positive, right? Because this would be negative times another negative, which means you're inside your square root, you're going to be doing tau squared plus something, okay? So think about this. Without that minus 4 delta, what do you have? You have tau plus or minus tau, right? The square root of tau squared would be tau over 2. But if this is positive, then the inside, this whole thing is going to be bigger than tau, right? Because without it, it's this tau squared is like tau. So if this was positive, this will be bigger. So then I would have tau plus something bigger than tau over 2. That would definitely be positive. And I would have tau minus something bigger than tau over 2. That would be negative. So you can conclude that if delta is negative, it's always going to be a saddle. It's always going to be a saddle. Okay. And you'll have real eigenvalues. There's no way, delta is negative, this whole thing's going to be positive, so you won't have any imaginary eigenvalues. Furthermore, if delta is greater than 0, then, and tau is negative, okay, so if delta is greater than 0, then what could happen? This could be real, this part could be real, or it could be imaginary, right? If I plug in a positive number in there. But in either case, whether this comes out to be real or imaginary, let's say they're imaginary, remember what we would do is split this up, and the stability would be determined by whether the trace was negative or not, right? If the negative part of the eigenvalue, the real part of the eigenvalues, if the real part of the eigenvalue is negative, it would be stable. So if tau is less than 0 and delta is greater than 0, you can also determine that it's stable. Again, it could be a sink or it could be a stable spiral. And then as we'll see going forward, sometimes that's all we care about, right? I mean, ideally, you'd want to know if it's a stable sink or a stable spiral, but if you at least know it's stable, that's important, right? So sometimes we don't really care. We just want to know if it's stable or not. Okay, all of this can be summarized in a diagram, which is in our book at the end of chapter 10.2. Okay, and this is a nice diagram to help you determine which of your 6 possibilities, your classifications for stability, you have. Okay, so the x-axis is tau, the trace. The y-axis is delta. Okay, now we saw on the previous page that if delta was less than 1/4 tau squared, it would be a real eigenvalues, and if you were greater than 1/4 tau squared, delta was greater than that, it would be complex eigenvalues. So the borderline, if you will, is when delta equals 1/4 tau squared. And so what I have here is that's a form of a parabola, right? Like y equals 1/4 x squared. So this is a parabola. Everything greater, so if I'm above the parabola, these are going to be spirals. And if we're below the parabola, anywhere in here or in here, then you're going to have real eigenvalues. Okay. So now we can distinguish even further. We saw that it would be stable, right? On the last thing we talked about was that if your trace was negative and your determinant was positive, that would be trace is negative, determinant is positive. That's over here in quadrant 2. And notice in either case, whether it's a spiral or a sink, both of those satisfy those requirements and they are both stable. Okay, and likewise, if your trace is positive, think about this. If your trace is positive, it could be a unstable spiral, it could be a node, and if your trace is positive, even if your determinant's negative, if your trace is positive, that would be a saddle, which is considered unstable. So there's a lot that can be learned just from the trace. If the trace is positive, it's automatically going to be unstable. Okay. Now, if the trace is negative, it depends, right? If the determinant is also positive, it would be stable. But if the determinant is negative, remember the determinant is negative. In either case, it's a saddle, right? Which is considered unstable. But essentially, you just have to figure out which side of the parabola you're on. Which region does the parameters you're working with, where does it put you on this diagram to determine what it's going to be? Okay, so let's try one here. Here's my matrix, -1, -1, 5, -3. I like to do the determinant first because as we saw, if the determinant is negative, it's automatically a saddle. Here my determinant is -1 times -3 minus -1 times 5. That gives me +8. So I know I'm above the tau line. Then I look at my trace. -1 plus -3 is -4. So that puts me, again, if my trace is negative and my determinant is positive, I've narrowed it down to either a stable spiral or a stable node. So in either case, I know it's stable. To determine precisely which one it is, I have to see which side of the parabola we lie on. And remember, the parabola's equation was delta equals 1/4 tau squared. So I would compute my delta. How does that compare to 1/4 tau squared? Well, 1/4 of -4 squared is 4. 8 is greater than 4. So that tells me my point is above the parabola, right? My parabola's equation is delta equals 1/4 tau squared. So if we're greater than that, we're above it. We're right here. And that indicates a stable spiral. Keep in mind, these conclusions can be verified. If you find the eigenvalues, you should be able to come to the same conclusion. But I think you'll agree on some of these. This could be much faster. For example, look at this next one here. -1, -2, 1, 3 is my matrix. Quick determinant calculation, -3 minus -2 gives me a determinant of -1, and it's over. I can already tell this has to be a saddle, because if the determinant is negative, it puts me in either one of these regions. It's going to be a saddle either case. So that's really fast, right? It would take a lot longer to do the minus lambda and do the whole quadratic formula. And then finally, here's my last one. My determinant is -1 minus -3. So that's really +2. But my trace is -1 plus 1 is 0, which means what that tells me, that puts me right on the y-axis, the delta axis above here. And if you go back to my diagram, that's the only situation where you get a neutral spiral, is if your trace is 0 and you end up on the delta axis. So this is a spiral, a neutral spiral.